We'll talk about Pauli matrix, and I want to review a little bit and finish up what we left there. So definition. So these are Pauli matrices. So we don't need to remember or understand the implication of physical meaning of Pauli matrix as long as we're dealing with the quantum computing. However, I want to emphasize there are several properties you do need to understand because it appears many times. So the first property is that, well, before I state the property, let me state some notation. So whenever I say sigma vector, so this is the notation I saw in a book by Mermin, and this is the vector of Pauli matrices. It's just symbolic notation, okay? And if I say n, which is just normal vector of real entries here, then I will write n inner product with sigma vector as just canonical, the formal inner product between these two things. So even though this is not a number, I just take the inner product as if these are numbers. So it's going to be A sigma x, B sigma y, and C sigma z. So it's just a linear combination of Pauli matrices. And the characteristic or the special properties about these matrices are they are antisymmetric. So it's actually skew symmetric, sorry. So it's skew symmetric. So what I mean by that is if you take the conjugate transpose, it is itself. Okay? So the x sigma x, if you take the conjugate transpose, there is no there's no imaginary part, so it's just itself, and also this part just itself, because it's a symmetric. It's a diagonal here. But also, if you take the conjugate transpose, you can see that it's the same thing. So, so that kind of matrix is called the Hermitian matrix. Now, the first property is that if I take the exponential of this matrix with the I theta here, then it's same as cosine theta I plus I sine theta and sigma. So here n. So almost same thing happens. So we show that when I have sigma x or sigma y, sigma z, it gets this way. But I'm saying that you can also replace that as n, a linear combination of these Pauli matrices. And another property is that this is what I mentioned the last time. So when I take any linear combination of Pauli matrix and make a unitary operator U with this exponential, then this is called 2 pi rotation. So it's not a definition. I'm saying that it's often called as a 2 theta rotation operator, or 2 theta rotation about sigma, so n sigma axis. So what I mean by axis is that we are looking at this operator geometrically in the 3 dimension. So we have sigma x and sigma y and sigma z. It's the same x, y, z axis, and the product between these Pauli matrices work as if they are the cross product between these standard bases. So if you see x times sigma x times sigma y, what is it? It's I times sigma z. Okay, so and then if you take the opposite, if you take the reversed order, then they get the minus I sigma z. Okay, so we can't ignore this work of I, because every time you multiply any of these two, you get I, but you can ignore it because whenever you multiply a constant, which is complex number of absolute value 1, what I said before, like 2 lectures before, is that it really doesn't make any difference whether you're working on the quantum state whose entire coefficients are multiplied with the same constants. So you can just think that these are just cross product. So what I mean by that, what I mean by the second property is that when you apply this unitary matrix, it's like rotation about some axis. Let's say this is your axis in here of every operators on this three-dimensional space. So I'm mixing up with the terminology, geometric terminology with the operator terminology. So let's look at the first one first. So why is it true? So although I'm gonna mention as a PF proof, but it's not really rigorous proof. I'm just mentioning ideas. So first of all, let's see what happens when you understand what this means. So basically, this is simply the formal formal series which follows the exact same series of power series of exponential. So we have I, theta, and sigma. So that's the 0th degree, first degree, and the second degree is I, theta, and sigma square divided by 2 factorial, and this goes forever. But now this is obvious, but it's just a matrix. And look at this one. So coefficient can be squared, no problem. What we have to do is square the sum of these Pauli matrices. So let's see what happens. A sigma x plus b sigma y plus c sigma z, and square that. But let's write again. To see what it happens. So when you do this expansion, you will get the square of each term. So we have a sigma x square up to c square sigma z square, right? But whenever you mix up the different terms, for example, a sigma x times b sigma y, there is a counterpart. You can choose b sigma y on the first factor and a sigma x on the second factor. So you switch the order of multiplication of two Pauli matrices, and what happens when you add them together? It cancels out, right? It vanishes. So there's nothing more than these squares. So of course, as I said, if you take the square of this, then you get the identity last time. So you can further simplify this thing, but let's see what happens when you multiply more. Let's say you have n of them. So you can easily imagine that this is simply becoming the nth power here, right? So you see why this follows. So again, you can collect all the real part to make cosine theta, and you can collect all the imaginary part to make a sine theta. And each of these, you can also split up the imaginary part into the one that has the sigma x as a factor and sigma y as a factor and sigma z as a factor. So this is why you get this. Okay. So, well, you can kind of imagine why it's called the rotation, because this is the actual formula of a complex number when you realize the complex number as a rotating map. So for example, if you have z equals to, let's say, let's drop the size, simply I zeta, then you can consider that to be a map which sends any complex number to another complex number by multiplying that on the left-hand side. And what it does is that if you have any complex number, it rotates by zeta degree. Okay. So whenever you want to multiply u of that form, then you can kind of imagine why it's okay, it's possible to say it's somehow related to rotation. But let's look at the second proposition more carefully. So why is it called the 2 zeta rotation? Why is not zeta rotation? So on the second part, so what we're going to do is we're looking at the Hilbert space of 1 qubit state, right? And what we are actually looking at, well, we're looking at the operator, which sends a 1 qubit state, which is a vector, to another 1 qubit state. But what we're really looking at is it transformed the entire Hilbert space, H1. So let's say I have that U, which transforms the entire Hilbert space. What I want to look at is not individual vectors, but I want to see how the operator is changing. So let's say we have our Z operator in our original Hilbert space, and I want to see what happens when I transform this entire Hilbert space into a new one. Although it's the same thing, but this every vector is now considered as an image of some vectors in the original space by the operator U. I want to see what happens to that Z operator after I do this. So to make it clear, I want to simplify my U to be exponential I pi over 2 sigma x. Okay. So my theta is pi over 2, and my Pauli matrix is just sigma x. So what is T then? So this T is the operator translated from the operator Z by the unitary matrix U. So it was originally Z, but because I translate everything in terms of U, so it's like you have a plane and you have a linear transformation of a plane to distort your grid of square grid into a parallelogram. It's like you want to push or you want to dilate in one direction, so you can make your entire plane like it has a horizontal and vertical axis, but after you translate, you get a different figure of your space. So in that different figuration, in that new Hilbert space, I want to see what this operator look like. So this T, so this is the standard diagram that you can see in many mathematical contexts. This is somehow commutative, so which means that if you take any vectors in here, it doesn't matter whether you follow this arrow or that arrow. Whenever you get to the same destination, you will get the same thing. So it means, so in that sense, we put this round arrow here. And also, I said this U is a unitary matrix, which means that it has an inverse. So if I want to go backward, then you can also take the U inverse here. So T from here to here can also go to the inverse direction of U and Z and then U. So you get the long detour here. So you get U is the T. So let's compute what T is. Zeta is 2 pi over 2 and sigma x and z and exponential I pi over 2 minus sigma x. So minus because we have a negative. Because if you have just sigma x, then it's commutative to itself. So you can take the inverse as by taking the negative sign there, because the exponential rule is true for exponential function. So anyway, let's see what this is. I will use the proposition 1. So our zeta is pi over 2. So cosine pi over 2 is 0. So we don't have the real part. So only the imaginary part, which is sine pi over 2, which is 1. So it's I sigma x. And this one is minus I sigma x, because sine. So in this case, this is understood as zeta equals to minus pi over 2, right? So it's not. So it's always any operator of this form is always this format. So everything else than I or Pauli matrix should go into the zeta. So what is this? So we have I and minus I, so it's 1. And z and sigma x. So sigma x just x. So zx is minus xz. So we can say sigma x equals to minus. So after I change these to order, sigma x z. And sigma x squared is 1, and you get the minus, so you get minus z. So then, does it make sense now? So what happens here, I had z, which is sigma z direction, and after I take the rotation or unitary matrix of that form, I change this to minus sigma z, which is minus z. Okay, so it's pi rotation, some kind of. But you can say, oh, maybe it's not a rotation, maybe it's just a flip. So let's try another one. So let's say instead of pi over 2, let's say I have exponential of minus, so plus pi over 4 sigma x. Okay. So I'm going to rotate by pi over 2. So let's see what happens. So the same z. Exponential I pi over 4 sigma x z exponential minus I pi over 4 sigma x. So what is it? So cosine pi over 4, 1 over square root I plus I sine pi over 4, 1 over square root, and sigma x, and that, and here it's same 1 over square root I minus 1 over square root sigma x. Okay, so let's expand this. Let's expand the first two. Yes, and we have 1 over square root 2z, and so sigma x is again just x, so we get x times z, and when you get x times z, you get I times sigma y, or just y, doesn't matter, and 1 over square root 2 I minus I 1 over square root 2 z sigma x, and let's expand again. So I think I can make it simpler here. So z times sigma y, is it right? So sorry. So it's not times, it's plus, right? So it's a plus I over square root sigma y, right? So, okay, so and then let's expand a little bit more. So we had 1 over 2 z and multiplying these two, I get minus I 1/2 z sigma x. Sorry, so z times, so not just sigma y. So here I'm having sigma x times z, so it's I times sigma y. Okay. So far what I did is expanding this one over here. Let's do this one over here. But there are two i's, so I can make it into -1. So minus 1/2 sigma y, and multiplying these two, I get plus I over 2 sigma y times sigma x. So what is sigma y times sigma x? So I need minus I times sigma z, right? No, just do I, right? No, sigma y. So sigma y first. Sigma y first, that means just I, right? So this is I sigma, no, minus I, right? Minus I sigma z. Because first row, first column entry is minus I. You have to multiply minus I. Then you need I. Yes, it's just plus I. So, okay, so plus. Okay, so plus. All right, so we have canceling out z, and we have y. All right, so let's go back to the picture again. So I translated z operator to y operator by applying this U gate here. So what happens? So before I had sigma z becomes minus sigma z when I have theta equals to pi over 2. But now theta is pi over 4. So I changed sigma z to sigma y, right? So I only had pi over 2 rotation. So I get the pi over 2 rotation in what direction? The clockwise direction. Normally we take clockwise direction as an opposite direction. So, but if you really want to translate everything in geometric way, then you have to consider of this operator as a 2 theta rotation in a counterclockwise direction, or clockwise direction, clockwise. So therefore, normally people sometimes use minus my theta, put minus up there, so that theta rotation is always counterclockwise. Okay? So it doesn't matter which direction, which way you take. So if you prefer this format, then remember that it's a clockwise rotation. And if you have a minus in your context, then remember that it's a counterclockwise rotation. So counterclockwise is that whenever you have certain so you have to choose your axis correctly. So I choose my axis so that it follows my right-hand rule. If you follow x times y, you get z. So in that orientation, this is always clockwise rotation. Okay. Sorry for holding up lots of time here. So any questions? Yes. What do you mean? Say it again. Yes. No. U is the rotation. U is the rotation, and T is the result of rotating Z operator by U rotation. So if you're only working with X, Y, Z operator, it's fine, okay? However, if you if you have only these operators, you cannot find square root of X or fourth root of X, which is, by mathematical setting, it's I sigma X, and this one is exponential minus pi over 8 sigma X. So if you want to really think about physical meaning of what this operator is, it is considered as an operator that rotates the entire axis of this Hilbert space. So it's just a different way of looking at our operators. So it's mathematically complete. There's no hole here, but maybe you can connect the physical meaning of this Pauli matrix and rotation. But as far as our computation concerned, this is what it is. Okay, so however, we're not going to use this kind of computation in the quantum computing. Most of the quantum computing only work with the what is given, which is just X, Y, Z, and some other swap operators and C0 gates. So we're not going to use this abstract settings in our real quantum computing. All right, so let's talk about one more thing, and then we'll get to the quantum algorithm. So I want to talk about some protocol called BB84 protocol. So if you really want to add one more category in the quantum computing business, there is one thing they called quantum communications. So it's about using quantum material or quantum information to transfer data or secure the data. And this protocol, as its name indicates, is developed in 1984. And I forgot the name of these two persons. BB stands for those names. And this tells that the quantum information is by its nature safe. Yes, it's safe, quantum safe. So what I'll tell you what it means. Okay, so here again, our Alice is here, and here we have a Bob. And here's another, I think you see this kind of picture many times here. So this is Eve. So Alice, so actually Bob wants to send a message to Alice, but Alice wants to make sure that the line is secure. So because there's an Eve always eavesdropping the communication channel between Alice and Bob. Okay, so this is the common situation that every time you have a cryptography. So it's always between the channel. It's about hijacking. So if you guys are in the two person in a room which have no one can ever hear about, then there's no need of secure. security or cryptography. But there's always we are assuming there is a person listening to our channel and gets all the information that they're transferring one person to another. So that's the problem. That's where the problem arises. So, if Alice sends Bob a message directly, then Eve can hear everything. So in the classical situation, then Eve can copy the entire message again, or manipulate or do something harmful on that message and send Bob a wrong message, or get the same message, but Eve has a copy of it. But now the situation when Alice is sending Bob quantum information, the situation is different. So remember, there is a theorem called no cloning theorem. So basically, it says there is no quantum gate that copies one quantum information or one quantum state to another. So what it means is that, okay, so if I have, let's say, plus cat, of course I can make a plus cat by applying a Hadamard or whatever. But suppose that we don't know what that is. Okay, we don't know what that is. So it could be 1/3 plus, let's say, so it's a 0 cat and 1 cat. It could be this, or it could be a plus cat. I don't know. There's no way I can copy in exactly the same quantum information to my quantum state. Okay, so only way you can see what's inside is by taking a measurement. But what happens when you take a measurement? The quantum states collapse. So you never get the original quantum state again. So you will never know. So once the quantum state is passed, if you take a measurement, it's gone, right? You cannot copy again and then take a measurement. If you could copy that, then you could have a guess that it copy lots of same quantum information again, take a measurement and again, and see how many times you observe 0 and how many times you observe 1. So then you can kind of guess what the size of the coefficients of cat 0 and cat 1 would be, but that's not possible. That's simply not possible, mathematically impossible. So what Eve can do at best, in hijacking the message from Alice to Bob when they are transferring quantum information, is that Eve hijacked the message that Alice sent to Bob, and then Eve take a measurement and then see what that is, and then mimic, or not even mimic, it just send the fake message to Bob. So that's the only way Eve can do when the eavesdropping. So even though that's a problem, so if Alice is sending a message like 0, 1, 0, 0, and so on, as if it's just a bitwise message, and if Eve drops this message and then gets all the information and send Bob the wrong message, that's the problem. So there's a clever way to detect whether Eve is eavesdropping the channel or not, which is called the BB84 protocol. So here is the start. So Alice prepares a lot of qubits and initialize to 0 cat. So it's easy to initialize 0, and then it's all known. It's even known to the Eve that Alice is preparing the original message. So it's not really a message, sorry. So it's a message, but it's not the real content of what Alice wants to deliver to Bob. It's just detecting whether Eve is hearing us or not. So anyway, so initialize this 0. And then the second stage is that, so you can see the list of the 0 cat. So you take so you can imagine easily by taking an light source as a quantum medium. So you can polarize your light in a certain direction, in the same direction for every light source or every photon you are going to send to Bob. And then Alice puts the Hadamard gate at random qubits. So random qubit doesn't mean that Alice forgets where the Hadamard is. So Alice always keeps the record where she put the Hadamard gates on each quantum qubits. So for example, it's always 0 at first, but let's say Alice put Hadamard gates in the following order. Okay, so I put I where she didn't put the Hadamard gate. So after applying this Hadamard gate, the quantum state becomes this. Right? So we can go forever, but I just show you some of the random first few quantum qubits here. And the third process is she sent that to Bob. Okay. Alice send them to Bob. Okay. So Alice could send actual quantum material to Bob, or she could have these quantum states stored in a photon or light source, and then with a light cable, send it to Bob. So usually it's light cable, so it's a light. So it's the best way to communicate long distance. And what happens to Bob is that Bob receives the message, and he has to read it quickly because the quantum material is going to have a decoherence quickly. So Bob, before he doesn't measure directly. So Bob also applies Hadamard randomly. So the quantum material is coming in from the wire one by one, and then Bob just randomly puts a Hadamard gate to each of the light source, whether he's going to put the Hadamard gate before measuring or not. Okay, and measure. I think I should put Bob's Hadamard gate right here. All right, so let's say Bob puts Hadamard gate this way. Okay, so what happens? So this was original message, the quantum message that Alice sent to Bob, and Bob applies the Hadamard. So it's plus 0, 0, plus 0, plus 0, where? Plus, right? So plus 0, right? And then reads it, okay? So, and then take the measurement. So when you take the measurement, there are certain state that is obvious what it's going to output. So 0 always read as 0. But when you have a plus state, you're not gonna always 0 cat. You can have a 1 cat. So let's say, just randomly, I put So this is the Bob's message. And then what happens? What happens? So Alice announced her sequence of Hadamard gates. So you can take a long break between 4 and 5, because if you do it simultaneously, maybe there's an eavesdropper, Eve, can kind of mimic this sequence and then confuse Bob. So it takes a long, I mean, not that long, but just a long time as long as Bob reads all the message. So Alice announced her Hadamard here, 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 and here. And what Bob does is match the place where his sequence of H matches to Alice's sequence of H. So which one is it? So here it matches here, and is it not? Okay, so only 2, right? So 1, 2, 3, 4. Yeah. Just so if you have more, then there are more Hadamard. So since Bob and Alice put H randomly, so I think at least 25% of the qubit has to have the same Hadamard gate on the same place, right? So what Bob does is, what happens to the qubit which has Hadamard gate on Bob's sequence and Alice's sequence, and ignored all the other. Or maybe he can just throw in more. For example, it had the same, so you can do the same thing here. So here, identity here. So, and the last one, I think, this one. Then also it has the no Hadamard. So having Hadamard or no Hadamard, either way, if Bob and Alice had the same sequence, then Bob keeps the record of the observation of that qubit. So what happens? Since the original sequence was 0, if you apply Hadamard twice, you get always 0. And also, if you didn't apply the Hadamard, then you also get 0. So it has to be always 0, right? So if Bob sees all the sequence that matches the Hadamard or not Hadamard with Alice is 0, then Bob knows that there's no eavesdropper. Why? Yeah, but why he can convince that there's no eavesdropper? So Bob knows that the line is secure. Why does Bob know that? How can Bob convince that there is no eavesdropper?
Measured the content before measured by Bob, then some of the Hadamard gate should be 1. But if the 1 goes to Hadamard again when Bob applies Hadamard, then it wouldn't be 0.
Yes, right. Cannot be 0. I mean, yes.
But what if
Right. Yeah. So yeah, both are good question and good answers here. So we have possibility of Eve to fake the message to Bob. So if she fakes and read the message of Alice and then give the fake message to Bob, and what happens in that case is Alice cannot make the exactly same information as Alice sent to Bob. It's impossible. So for example, Alice doesn't know whether even if she reads 0, the original quantum state was 0 or plus state, or even minus state sometimes, right? So the measurement itself doesn't tell you what the original quantum state was. So it could be just lucky to get the 0 after having a 50-50% chances of having 0 or 1, or it was just 100% 0. Eve doesn't know. So, and also, since there is no cloning theorem, Eve cannot copy the entire message. So all Eve can do is just fake message. So fake means that it's not closed, anywhere close to the original message that Alice sent to Bob. It's just random, another message. So Eve could randomly put zeros and pluses in her fake message to Bob. But in that case, what happens in Bob's situation is when Bob applies Hadamard, he doesn't know where Alice put Hadamard or identity operators. Even Eve doesn't know. No one knows. Only Alice knows. So Bob should put the Hadamards or identity gates in random positions. And in that case, there should be some chances that some places we're not going to be 0 after applying the Hadamard because the entire message is just simply different from Alice, right? So we'll not guarantee that you get 0 state, the 0 state. So if Bob, so there is a big assumption here. You shouldn't have any error in the measurement or any noise in the transmission and transmitting the data. So if the data is by its nature altered because of the noise in the channel or physical thing, then you have to take in consider it could be a noise. It could also be because of the presence of Eve, but you have to take some kind of threshold whether if you even if you read some ones in all the places where Eve, Alice, and Bob had the same gate, you could have a measurement of 1, but it could be it can be neglected because it's too small. But if Eve faked the message, then you should have lots of 1. So practically, you should have almost 50% of the message that you read from these places should be 1, right? So if you have lots of messages, like lots of qubits in a series, then you have more places where your gates, Bob's gates and Alice's gates are the same. And then you have lots of zeros after you take the measurement, after Bob takes the measurement, if there's no Eve. But if there was Eve, then you cannot avoid the chances that there are many, almost 50% of these qubits are read as 1, right? So in that case, so you see lots of 1s. Okay, this shouldn't be because of a noise or errors. It should be someone who faked the message. And what happens then? You know the presence of Eve. Well, you cannot do anything to Eve, right? So what happens is you change the channel. You change the transformation channel. Okay. So you don't want to transfer the data or message through that channel. So you do the same thing with the other channel and see if there's no one listening. And then if you take if you're convinced that there's no Eve, then you transmit the real data. So this is not about cryptography. It's not encrypting the message. It's not encrypting the message. It's just checking whether the line is secure. Okay. So when people say the quantum communication is by nature it's safe, and that's what it means, because it's not possible to copy the message. Okay. All right. So any more questions? So we want to move on to a different, well, not really different, a new topic here. So we want to get into the real quantum algorithms. So that's the fun part. We could talk about quantum circuit, but the quantum algorithm will contain the material that we need to know about the quantum circuit. So let's get right into early quantum material, early quantum algorithms. There are several, and the funny thing is that there are not many quantum algorithms, effective quantum algorithms until now, and these are all developed around 1990s, even go back as late 1980s. Anyway, so one thing that you have to be careful about is whenever we talk about the quantum algorithm, it involves an oracle. So what is an oracle? So an oracle is, so it's a quantum gate that has input and output register. So you can, so register is a terminology that often appears in the quantum computing business. You can understand the register as just the quantum qubit, or you can understand it as a wire or whatever. So you'll see what it means, because I'm going to use it a lot in the context here. That's determined by so it's often determined by some function. So I think that's as far as I can explain. Let me give it an example of oracle, and you see what it means. So let's think about a function that sends 1 or 0 to 1 or 0. Okay, so it sends so the domain is 0 and 1, and the codomain is also 0 and 1. So it's a 1-bit function. There are 4 possible ways to define it, right? So we have x 0, 1. So f of 1 could have 0, 0. F of 2 could have 1, 1. F of 3 could have 0, 1. F of 4 could have 1, 0. There are 4 possible ways of finding such function. These are all 4. And what does quantum oracle look like? So we have, let's say y here. The quantum oracle right here, the unitary gate, that has 2 quantums as an input. But really, you take the 2 quantum state, 2 qubit state as an input, or something that you want to translate through this quantum gate. But we call this x to be the input register and y to be the output register. So that's something that everyone who introduced the quantum oracle or quantum circuit the first time get confused about. So what happens is the input gate doesn't change. Input gate doesn't change. But the output gate, so this is one way you can change the output register. Let's say is changed by y plus f of x cat state. So what does that mean? So in this case, so since remember that this is not the definition of the abstract oracle, it's just an example of oracle with respect to this function. So, and also x and y are either 0 and 1. So it just describes the special situation when you have your input register and output register initialized at base cat state into 0 cat or 1 cat. And this O plus means that it's a binary addition. So this whole thing is also 0 and 1. So let's say we have f equals to f, let's see, 1. What happens? So UF1, if I have input and output register initialized at 0 cat, the input register doesn't change. The output register also doesn't change, right? Because F10 is 0. So I add 0 to 0 to get 0. So how about what happens? I have F2. Okay, so F2. So when I have 0, nothing happens to the input register. When I have 0 on the output register, it changes to 1 because F20 is 1. So at 0 to 1 is 1. So it changes this way. So someone might ask, it's quite different from the classical computer because classical computer always have one input and one output, right? Why do we have to put the input and output at the same time and also get the input and output after applying this oracle? Now that's the beauty of the quantum algorithms. The input register and output register does something to get the information about this function. So here is a definition of a problem. So it's a Dutch problem. Classify the function from 0, 1 to 0, 1, the same function above here, into balanced or constant. So these two are constant, and these two are balanced. You see what it means? Constant obviously is constant. Balanced means that the number of outputs are the same. So 0 and 1 are always just 1, 1, and 1, 1 here. So 1, 0, 1, 1, and 1, 1, and 1, 0. So how many times do you have to read the value of function to find out whether the function is balanced or constant in classical computer? You have to take the value of function twice at x equals to 0 or 1, right? Nowhere you can find by one query of the function to find whether it's balanced or constant. So Dutch's algorithm is the quantum algorithm to solve this Dutch's problem in a faster way than the classical computer. So it's not really dramatically faster than classical computer because classical computer only needs 2, but Dutch's algorithm, which is quantum algorithm, needs one query of the function. So actually not a function, it's oracle. So definition. Dutch's algorithm says that, so we're having the same oracle here. So we're gonna put the input register at 0 and output register initialized at 1 cat, and put the Hadamard gate on both of them, and then apply the oracle, and then Hadamard gate again, and take a measurement. So that's the DGIST algorithm. That's the quantum circuit that implements DGIST algorithm. So when I put this special cat state into the beginning of the quantum circuit, it means that it's initialized at this cat state. So you have to think of this circuit. So this is the picture of diagram of the quantum circuit. You read from the left to right, and you can imagine that the time is progressing from left to right too. So here I don't think I have time to go through all these steps here. And you have 0, 1, 2, 3 stage. So let me do it quickly. So here, psi 0 is first initialized at here, and psi 1 is now changes to Hadamard state. So we have Hadamard applies the Hadamard gate, so it changes to this. And let's expand this. So we get 0, 0 plus 0 minus 0, 1, and 1, 0, and 1, 1, right? Again, now oracle, even though I mentioned the oracle works that way when x and y are 0 or 1, it's a linear transformation, so it can work on the superposed state. So let's see what happens after I take the oracle here. So I don't know what the function is, because that's the catch. So first it becomes 0 f0 minus 0 f1 plus 1 f0 and minus 1 f1. Sorry, made a mistake here. So 0 is right. So this 0 is the input. So I have to add 1 to f0. So when I add 1 plus f0, it's always the opposite number to f0, right? If f0 is 0, then it becomes 1. If it's 1, then it's 0. So by meaning that, I put the bar here. So that means whatever I get as f0, it's the opposite, okay? And how about this? So we get f1 because it's 0, it's the same thing. But here I get f1 bar here, okay? Now, we're not gonna finish. We're not gonna measure until I apply the Hadamard again to the input register. So psi 3 is, what is it? So it's plus f0 minus plus f0 bar and minus f1 and minus f1 bar. Let's expand this more. So how I'm gonna expand is collect all the state where the input register is at cat 0. So think about the calculation, think about the quantum state in your head, and it has f0 here, and cat 0 here, but minus f0 bar, and here it has a cat 0 but plus, and you have a cat 0 but minus. Okay, so that's when the first cat is first input register is at 0, and also think about, oh, so I forgot to square root here. 1, so it has f0 minus, so now plus, okay, so it's minus f0, and then we are talking about the 1 cat here, so 1 cat has a minus sign and the minus cat, so have minus f1, and then also minus minus is plus f1 bar, okay? So that's the size 3 state. And what happens at the end? The measurement. M stands for the measurement. I take a measurement on what? Which register? I take a measurement on input register. That's a weird thing because I changed the output register. Why not taking a measurement on the output register? It actually happens when I take a measurement on the input register, I get some information. So let's say I had take let's see what happens in these four cases. So if it's constant, what happens? If it's constant, F0 is same as F1, right? Whether or not it's 0 or 1, F0 is always same as F1. So these two cancels out. And these two also cancels out, right? But these survives. This part survives. Whatever that is, it's going to be plus or minus, whatever. It survives here. So when F is constant, there's no chance you can read 1 in the input register. So in other words, if you read 0 in the input register, it means that your function must be constant. Let's think about other ways. Let's say we have a balanced function. Balanced means that F0 is different from F1. So in that case, F0 and F1, F0 and F0 bar is the same thing. I'm sorry, it's not the same thing. So where am I? F0 and F1 is different. Therefore, F0 and F1 bar is the same thing, right? Because if F is balanced, F0 and F1 is different, but then F0 and F1 bar is same thing. So these two cancels out, and these two also cancels out. So this second part survives. So there's no chance you can read 0 in F is balanced case. You always get 1 when you take a measurement on input register. So by taking a measurement and input, you see which category of this function is. So you only need one query of the function, oracle, instead of 2 when you have a classical situation. Okay, so I think we don't have time to go more. So next time we'll talk about more if you have questions. Also, I'm going to introduce another quantum algorithms. See you on Wednesday.